on the Math Guy Steve. Let's try evaluating this integral. So when evaluating integrals, there's a few different methods or different approaches to evaluating integrals. Oftentimes you want to try using a U substitution if that's possible, mainly because it's just a lot easier for you to use. Okay. And so here, this one actually can be done using a U substitution, which I did in a different video. But here, also, when we see that square root with two terms underneath the square root, oftentimes this kind of lends to or hints to maybe possibly integrating this using a trig substitution, okay? So for this one, we'll use a trig substitution. So for this one, we'll say let x equal 3 sine of theta. Okay. All right. Then we have to put something in for every other part, right? So we have to kind of create a sub bubble. I call it a subble. Okay. Meaning, if x is 3 sine of theta, then what does this create? Well, then we know that x over 3 is the sine of theta. So dealing with our trig, we know from SOHCAHTOA, we can make a right triangle here, not a left one, or not a wrong one either, a right one. Okay. All right. Where we have a right triangle, let theta be here. From SOHCAHTOA, we know that the sine is the opposite of the hypotenuse. So this would be x, and this would be 3. By our Pythagorean theorem, then we know that this ends up being the square root of 9 minus x squared. All right, then we have some other parts to fill in. Okay, so that is, if x is 3 sine of theta, then dx is taking the derivative of each side. 3 times the derivative of sine of theta is cosine of theta. D theta. We know that then the square root of 9 minus x squared, we'll plug in something for that. And we get, that's the square root of 9 minus, what we just said, this x is 3 sine of theta, so 9 minus 9 sine squared of theta. By factoring, we get this is the square root of 9 times the square root of 1 minus sine squared of theta. And of course, 1 minus sine squared, we just said, is cosine squared. So we get 3 times the square root of cosine squared of theta, which is 3 cosine of theta. Okay. All right, so I have something to plug in for x, something to plug in for dx, something to plug in for that square root. We need something to plug in for this x cubed as well, right? So we know if x is 3 sine of theta, then x cubed is 3 cubed sine cubed of theta. In other words, that's what, 27 sine cubed of theta. All right, so we have something to plug in for each part. Here's our sub bubble. Here's our subble. And now let's plug. We end up with, okay, so the integral of x cubed is, we'll plug in 27 sine cubed of theta. Okay. For that square root of 9 minus x squared, we said we're going to plug in 3 cosine of theta. So times 3 cosine of theta. And then for dx, we said that's 3 cosine of theta. So another 3 cosine of theta d theta. And hopefully this is an easier integral to integrate. Now, because of the linearity of integrals, we're allowed to take those constants and bring them out in front. Okay, so that's 27 times 3 is 81 times 3 is 243. 243 times the integral of sine cubed of theta, cosine squared of theta, d theta. And hopefully this is an easier integral to integrate, which it is. It is, okay? All right, so sines and cosines, we always look for which one is odd, right? We can kind of pull that off and we'll make a U substitution out of it. So like here, we have a sine cubed, right? So we'll take one of those signs and kind of pull that off, let that be the du in our U substitution. Okay, so here we'll say, okay, well, let U be the other one, right? So let U equal cosine of theta, okay? Then the du will equal derivative of cosine is negative sine, so negative sine of theta d theta. Now that negative we can kind of manufacture, so that means that negative du is sine of theta d theta. Okay. So here's our U substitution, essentially. So here's another sub bubble that we have. Okay, another subble. There we go. Okay, and then from there we'll say, well, our original integral was 243 times the integral of, but now we'll take that sine of theta off. So this becomes sine squared of theta, or cosine squared of theta, right, times that sine of theta d theta. So we have something to plug in for sine of theta d theta. That'll be the negative du. Okay, for the cosine squared, we'll just call that u squared. But then for this sine squared, well, we can use what we did earlier. And that is, we know sine squared is 1 minus cosine squared. Okay, so this becomes 243 times the integral of 1 minus cosine squared of theta, right? Times cosine squared of theta times sine of theta d theta. Now we can use that substitution. Okay, so again, we know that, so this becomes 243 times the integral of. Now we get 1 minus cosine squared, so 1 minus u squared, so 1 minus u squared. Cosine squared, so that's u squared. And now again, for this sine of theta, d theta, we know that's negative du. So I'll put the du here and take the negative, pull it out in front, again, because of that linearity. Again, hopefully this is an easier integral to integrate. It is. It is. We can distribute this u squared across the parentheses, so negative 243 times the integral of u squared minus u to the fourth du. And now it's just a couple of power rules, right? From our power rules of integrals. So we get, okay, that's negative 243 times, okay, the integral of u squared is, again, by our power rule is u to the third divided, so 1/3 u to the third minus 1/5 u to the fifth. Again, once we're done integrating, don't forget that plus c, okay? So plus c, right? Distributing is negative 243, we get negative 243 over 3 is 81, right? So negative 81 u cubed. Distributing negative 243, we get plus 243 over 5 u to the fifth plus c, okay? But again, that's not our end, right? We're done integrating, kind of, except we have to simplify this, or more so, we made up that u stuff. The x is by x stuff. So we have to back substitute what u was. Let's go back, okay? We saw that u was cosine of theta. Got it. So in back substituting, we get that, okay, if u is cosine of theta, then that means that this is negative 81 cosine cubed of theta plus 243 over 5 cosine to the fifth of theta plus c. Got it. But again, we didn't start off with thetas, we just started with x's. We made the theta stuff up too. So let's go back to that original triangle that we had, because that kind of helps us out, right? So in our triangle, we saw that, okay, we had theta here, x3, and then the square root of 9 minus x squared. So that gives us a better visual of what cosine of theta is, right? So we had, here was theta, here's x, here's 3, and here's the square root of 9 minus x squared. So if I need the cosine of theta, the cosine, remember, by SOHCAHTOA, we know cosine is the adjacent over the hypotenuse, right? So that would be square root of 9 minus x squared over 3 is our cosine of theta. So this becomes negative 81 times the square root of 9 minus x squared over 3, all cubed, okay, plus 243 over 5 times that same cosine, so the square root of 9 minus x squared over 3 to the fifth power plus c. And now simplifying, okay, we get, so this is, if I cube a fraction, you cube the top, cube the bottom, right? So this is negative 81 times, now cubing the top, this is, the square root is a half power, so this is 9 minus x squared to the 3 halves now. And then cubing the bottom, we get 3 cubed is 27. So divided by 27. The top raises to the fifth power. So that's 9 minus x squared to the 5 halves. And then divided by our times 3 to the fifth is 81 times 3 is 243. So over 243 plus c. Now these 243s end up canceling. And here this simplifies to just negative 3. So negative 3 times 9 minus x squared to the 3 halves plus 1/5 of 9 minus x squared to the 5 halves plus c. Okay. The good thing about integration is that it's always checkable, right? We can always check this by taking the derivative with respect to x of this ending expression and show that we get the original integrand, okay? So that's our Nike step, our check step. Or we can even check it by integrating this a different way, right? In a different video, I showed how to integrate this by a u substitution rather than a trig sub, okay? But again, integrals are difficult. They do have a lot of things going on, a lot of different methods, but I always try to use what's best, okay, for that specific integral, okay? And always remember, math is everywhere.